You are welcome to the lesson on atomic absorption spectroscopy, popularly known as AAS. As we look at this lesson, don't forget to subscribe, like, comment, and share this video. Click on the subscription button and share it with your friends, your colleagues, your children, your loved ones, and your students. In the 19th century, Robert Wilhelm and Gustav Robert Kirchhoff, both professors at the University of Germany, discovered spectroscopy, which is a scientific technique used to study the interaction of matter and radiation. Spectroscopy focuses on measuring the absorption, transmission, emission of radiation by atoms or molecules as a function of frequency or wavelength. It provides information about the energy levels, structures, and properties of molecules. The modern form of atomic absorption spectroscopy, generally known as AAS, was largely developed during the 1950s by a team of Australian chemists. They were led by Sir Alan Welsh at the Commonwealth Scientific and Industrial Research Organization, CIRO, Division of Chemical Physicists in Melbourne, Australia. Atomic absorption spectroscopy is used for the study of elements and metalloids. The objective of these lessons, by the end of this lesson, the student should be able to define AAS, know the different types of AAS, know the various parts of an AAS, and describe the functions of the various components of AAS. AAS is an analytical technique used to determine the concentration of specific elements or metalloids in a sample. In AAS, atoms absorb light at a specific wavelength, and the amount of light absorbed is proportional to the concentration of the element. The concentration of the elements are determined from a working curve after calibration of the instrument with standards of known concentration. That will be in our next lecture. The samples measured are usually liquid or solid. It is simple and easy to use. What are the types of AAS? We have the FAAS, that is the flame atomic absorption spectroscopy. It uses a flame to atomize the sample. We have the graphite furnace AS, GFAS. It uses a graphite furnace to atomize the sample. It is more sensitive than the FAS. We have the hydride generation AS, that is HGAS. This uses a chemical reaction to generate volatile hydrides suitable for elements like arsenic, selenium, and antimony. We have the co-vapor AS, CVAS, uses chemical reaction to generate mercury vapor specific for mercury analysis. We also have the electrothermal AAS, EAAS. It uses a graphite furnace and other electrothermal atomizers, similar to GFAAS. We have the Zeeman AAS. The Zeeman AAS uses magnetic field to split absorption lines, improving background correction. We have the atomic fluorescence spectroscopy, AFS. This measures fluorescence instead of absorption, more sensitive than AAS. We also have the inductively coupled plasma AAS. This uses an ICP source for atomization and excitation and is highly sensitive and multi-elemental. We also have the direct current plasma AAS, DCP AAS. It uses a direct current plasma source for atomization and excitation, less common than ICP AAS. Note that each type of AAS has its own strength and limitations and applications depending on the sample type, elements of interest, and desired sensitivity. What are the components of an atomic absorption spectrophotometer? Is as shown on figure 1 of a schematic diagram of the AAS. We have the halo cathode lamp, we have the chopper, we have the sample, we have the oxidant and the fuel, the flame, the monochromator, the detector, the amplifier, and the readout. We take each of these individually. We are now going to talk about the light source. The light source uses the argon or neon gas. The halocathode lamp emits narrow spectral lights of wavelengths, characteristics of the element to be determined. Each element has its own unique lamp, which must be used for that analysis. We have the electrolyte discharge lamps. Uses a radio wave or radio frequency field to excite a gas, typically argon or nitrogen, which produces a plasma. We also use the deuterium lamps. They are an electric discharge to excite deuterium, an isotope of hydrogen. And we also have the xenon lamps. This uses an electric discharge to excite xenon gas. All these lights are used as light sources. All these light sources in different spectroscopies. There are two main types of spectrophotometers. According to the light beam, we have the single beam, and then we also have the double beam spectrophotometer. The single beam is the one that works with the total light projection that passes through the sample. And the double beam is divided into two parts. One part passes through the sample, that's the sample beam, and then we'll have also the reference beam. The reference beam measures the absorption. The sample beam can be compared to the reference beam. Therefore, absorption is the ratio between the sample beam and a reference beam. We have the chopper. The chopper is usually a rotating wheel or disc with a specific pattern, or slots or holes, which creates the modulation effect. The purpose of the chopper is to modulate the light beam at a specific frequency, maybe from 200 to 1000 Hz. It allows measurement of absorbance. It helps to reduce noise and interference. It improves signal-to-noise ratio and enhances analytical sensitivity and accuracy. In this atomic absorption spectrophotometer, we'll have where we put the sample. The sample is introduced into the atomizer. The atomizer is either a flame or a graphite furnace. And the sample is heated to a high temperature, breaking down molecules into atoms. The atoms are vaporized, creating a cloud of atoms that are exposed to light. The sample can be liquid, like water, blood, or urine. Can also be solid, like soil, tissue, powders, and it can be gases like air or industrial emissions. It can also be semi-solids, slurries, or suspension. It can be metals, sodium or potassium. It can be heavy metals, lead or mercury. It can be nutrient elements, nitrogen, phosphorus, potassium, and it can be toxic elements like mercury, arsenic. So the concentration can be determined at the parts per million level using this spectrophotometer. AS can be used to determine over 70 different elements in solution or directly in samples, directly in solid samples through electrothermal vaporization. We also have the oxidant and the fuel. The oxidant and the fuel, we have the air acetylene mixture as oxidant and fuel, and we also have the nitrous oxide acetylene mixture when a hotter flame is required using a premise burner. Atomization takes place in a burner. Burners are mechanical devices that burn gas or liquid fuel into flame in a controlled manner. We have different types of burners. We have the total consumption burner. We have the partial consumption burner. We have the slot burners. We have the ceramic burners. we have the Tasson burners, we have the boosted discharge burner, and then we have the nitrous oxide acetylene burner, often for GFAAS. The burners play a crucial role in AAS as it affects the atomization efficiency, sensitivity, and accuracy of the analysis. What are the types of atomizers? We have the flame atomizer, uses flame to heat the sample, usually for liquid samples. We have the graphite furnace atomizer. This uses a graphite tube heated by electric current used for solid or viscous samples. We have the electrothermal atomizers. It uses a heated filament or tube to atomize the sample, useful for trace elements like cadmium, selenium, and arsenic. And then we have the heavy metals, or we can also use it for them, copper, nickel, and cobalt. We can also use it for toxic elements like arsenic and lead, and for nutrients like copper, zinc, and iron. We have the cold vapor atomizer. This uses a chemical reaction to produce mercury vapor, is specifically for mercury analysis. We have the monochromators. That is the prism or grating. It selects and filters the spectral lines emerging from the halocathode tube. It provides the desired wavelength out of the range of wavelength emitted by the source or analyte. A prism is usually used, a transparent material like quartz glass that reflects light. We use quartz prism due to its transparency and thermal shock. We can also use a grating, a surface with parallel grooves that diffract light. We can use mirror to redirect the beam and filters to block unwanted wavelengths. In the spectrophotometer, we have the detector. The detectors are photomultiplier tubes. They are most widely used. We have the photoiodides, used due to their high sensitivity and stability. We also use the charge-coupled device for rapid multi-element analysis. We have the diode array detectors, which are multi-element. And then we'll have the fast photo multipliers tubes, and we'll have the optical fiber detectors, allow for remote sensing and reduce interference. The detectors are very important because these detectors convert the absorbed light into an electrical signal, which is processed and displayed as an absorption spectrum of peak intensity. The choice of detector depends on the specific instrument, sample type, and analytical requirements. We also have the amplifiers. The amplifier helps to increase the sensitivity of the AAS. It improves the accuracy and precision of the measurements. It enhances the detection limits for trace elements. It reduces the effect of noise and interferences. We have different types of amplifiers. We have the trans-impedance amplifiers, operational amplifiers, and then we have the lock-in amplifiers. So we're saying that we have the readout devices. The readout devices are the analog meters, the digital displays, we have the computer screens, we have the printers, and then we have the data acquisition systems. We'll have the reader device could also include charts, recorders, and it could even have a microprocessor so that by a touch of a button, everything is coming out. We'll have the experimental condition, the observant data, the statistical values and calibration costs can be obtained through modern equipment. And the reader device is an essential component of AAS as it enables the user to interpret the result and make informed decisions based on the analysis. So, in summary, the different components of the AAS are the halocathode lamp, the chopper, the sample, the oxidant and fuel, the flame, the monochromator, detector, amplifier, and Readout Devices. It is important that we learn about these components as shown in the schematic diagram in figure 1. The figure 2 here just shows us an example of an AAS. There are several examples, but I've just picked this one to show us what a small AAS looks like. We'll have the study questions. List the different types of AAS and their functions. Explain the types of atomizers and their uses. And AAS is an important tool for analysis. Discuss. Next lecture, we'll be looking at how we can analyze our sample using AAS. Today, we have been able to show us or tell us the different components of an AAS. How do we analyze our sample? What are we expected to do when we want to use this instrument? I expect it to be part of the next lecture. And I thank you very much. But don't forget to subscribe, like, comment, and share this video. Share it with your friends, share it with your students. This video will help them. These are topics that we learn in analytical chemistry. They should not fail to follow my channel. Please subscribe to my channel and see you in the next class. Thank you very much.